So the next method we'll talk about is the Poisson distribution. So the binomial distribution asked a series of yes or no questions, and the number of yes or no questions was apparent from the beginning. So we could count the number of yeses and nos, and we can know how many times we tried to count. So Poisson works a little different. So Poisson describes events in time and space, and that means that there's an area of opportunity for things to happen. So a lunch hour, for example, that's a 60-minute opportunity for people to show up and get lunch. And it's not really a series of yes or no questions, but really asking for the number of times a particular thing happened in the area of opportunity. So if I could ask, how many cars do I expect to come to lunch, or what's the chance 17 or fewer cars come during the lunch hour? You could do this, and this describes all events in time and space subject to a few assumptions. And so, for example, we can model chocolate chips falling on a cookie as a Poisson distribution. So if you were Chips Ahoy and you were trying to do statistical process control on your chocolate chip deployment, you would use a Poisson distribution. If you had a refrigerator that was moving through a manufacturing process, if the opportunity to get dented increased linearly with the surface area of the fridge, it would be a Poisson distribution. So every square inch of fridge is a chance for it to catch a dent on its way through. So the Poisson distribution is important because there are many situations in business where we're looking at events over time or space. So let's suppose I expect 3 cars to arrive per 15-minute block to a drive-through window. So my average arrivals is 3. And notice this would be something you would estimate from historical experience. And that's true of all Poisson processes. You need to know the average amount of events in your window of interest. So what's the typical number of dents in the fridge? And it's the average, not the median, so you can have decimals. So if I dent one fridge out of 100, then my average will be something like 0.01. So every fridge gets 0.01 dents. So in that context, fractional things make sense because we're talking about an average over an aggregate. So if I expect 3 cars to show up on average, I can calculate the probability of getting exactly 3. And you would do that by, you need to plug in the number that you want to happen, the number that you expect to happen, and then whether or not it's cumulative. So on the side here, I have Poisson 5, 3, 0. This is the probability that we get exactly 5 cars for lunch. 5, the average is 3, 0 means we're not doing or less. If I put a 1, 5, 3, 1, that would be the probability I have 5 or less cars for lunch, which would be pretty high. So even though the average is 3, 2 and 3 are the most likely because as we move into 4, 5, 6, 7, 8, there's no limit on the number of things that can happen. They just become increasingly unlikely as the number increases. That creates a right skew to the distribution, and which means the typical experience might be somewhat less than the average. So let's do an example here. I'm going to switch back to my thing. So suppose I want to know the probability that a automobile has 2 or more physical defects after assembly. Assume 0.4 on average. Okay, so we want 2 or more physical defects. So I do Poisson, P-O-I-S-S-O-N, or Poisson.dist. So x is the target number of events. So if we wanted to do exactly 2 events, we would type 2. The average number is 0.4. Now if I put a 1 here, this would be 2 or less. And if I hit enter, I'd get 2 or less. But it doesn't ask for 2 or less, it asks for 2 or more. So the opposite of 2 or more is 1 or less. So I'm going to replace the 2 with a 1. Now I'm doing 1 or less. And if I do 1 minus, now I'm doing the complement of the probability of 1 or less, which is what I'm after. Right? 1 or less, the opposite is 2 or more, that's what I want. So the probability of getting 2 or more physical defects with a 0.4 on average is 6%. So not very likely, but then if you've got an average of 0.4, getting 2 is, definitely on the high side. So that's the Poisson distribution. So you can distinguish it from the binomial distribution a couple ways. So the binomial distribution, to use it, you need to know the probability of getting a yes. That means a decimal is required, and the decimal will be a probability between 0 and 1. Poisson, you don't necessarily need a decimal. You might get one. Your average might be a decimal, but it may not be between 0 and 1. In fact, most cases it won't be. So in this case, it just happened to be between 0 and 1, but this is not a probability. 0.4 is not a chance. 0.4 is just the average. So you can spot them that way.